Honors Chemistry. This is the Lesson 15 Activity Series, and this is the instructional video for that lesson. So the first thing we're going to do is go over the 5 fundamental types of reaction that are used in chemistry. The first one is called a combination or synthesis reaction, and that combines 2 or more elements or 2 elements or compounds into a single compound. So there's an example below of 2 things being combined into 1. Next is a decomposition reaction. So decomposition reactions break one compound into 2 or more products. So you can see that's just the opposite of a synthesis reaction. So you're taking one reactant over on the left and turning it into 2 products over on the right. Third is combustion reactions. We've seen these quite a few times in class. So combustion reactions combine hydrocarbons and carbohydrates with oxygen, and what the products are from that combustion is to produce carbon dioxide and water. So essentially you're burning something. You're using oxygen, a hydrocarbon or carbohydrate. You can light a match to it, if it's a hydrocarbon in particular, and cause it to burn. Double replacement reactions substitute 2 cations with 2 anions. What they really do is they switch the cations. So if you just look at what's going on here, the potassium K initially is with SO4 sulfate, and it switches places. It moves over and it joins up with iodine. The calcium, which is originally with iodine, switches and moves over to join the sulfate. So the K and the Ca switch places is essentially what's happening here, and that's called a double replacement reaction. And we will use double replacement reactions to study something called net ionic reactions in a few weeks. Finally, the 5th of the types of reactions is called a single replacement reaction. So single replacement reactions substitute a metal element for the cation in an ionic bond. So there you see calcium sitting as a lone element out there. It's electrically neutral, has the same number of electrons as protons, no charge to it. And then you see an ionic compound with zinc. And zinc is positively charged. It's given up 2 electrons to the chlorine. The chlorine has gained the 2 electrons, so that means the chlorine is negatively charged, the zinc is positively charged. Together they're electrically neutral, but the zinc itself is a 2 plus. It's gained 2 electrons. So what happens then is the calcium and the zinc trade places. The zinc comes out and becomes an electrically neutral atom, same number of protons as electrons, and the calcium joins up with the Cl2. So we're going to talk about how that happens, what's going on here. So to understand single replacement reactions and whether they'll take place or not. In the last case, will the calcium and the zinc trade places or won't they? We use something called the activity series. And it's almost kind of a table of lower electronegativity, lower ionization energy elements. Going down the list, you go to higher electronegativity, higher ionization energy elements. So the activity series identifies which elements will react with an ionic compound to create a single replacement reaction. So if the lone element is above the cation in the ionic compound, then the reaction takes place and the lone element will change places. If the lone element is below the cation in the ionic compound, then the reaction will not take place. So we'll see several examples to kind of clarify this. Let's understand why this happens. Let's take a look actually back at this again. If you look at the elements up at the top there, lithium, potassium, barium, calcium, and sodium, those come from the left side of the periodic table, the alkaline earth metals. They are the weak guys. We always said they were the weak guys. They have low ionization energy, meaning they easily give up their electrons, and they have low electronegativity, meaning they don't pull in outside electrons. So those are the weak guys. Now in ionic bonds, we always talked about The strong guys being over on the right side. Those are the non-metals. Those would be things like oxygen, fluorine, chlorine, sulfur, and so forth. Those are strong guys. They have high ionization energies. They don't give up their electrons easily, and they have high electronegativities, meaning they're good at pulling in electrons from other elements. So here up at the top, you see the really weak guys that we've talked about: lithium, potassium, barium, calcium, sodium, and so on, way over on the left side. But what you see as you go down that list is not the strong guys, the nitrogen, oxygen, fluorine, chlorine, but you see more metals. You see transition metals: iron, cobalt, nickel, tin, lead, copper, silver, mercury, platinum, gold. Those are the metals from the middle of the periodic table. So when you think about this, those metals down at the bottom, while they're not strong guys, they are stronger than the ones up at the top. The really weak guys are over on the left side of the periodic table, the ones up at the top. The ones in the middle are not strong guys, but they're stronger than the ones over on the left side. So what that means is they do have a tendency to pull electrons away. The elements down here on the bottom, which are transition metals, do have a tendency to pull electrons away from some of those elements up on the top, which are the real weak guys, alkaline earth metals. So what that means, for example, if you look at iron, which is about halfway down the list, it could take an electron away from lithium in a single replacement reaction, lithium being up at the very top. But it can't happen the other way around. Lithium is too weak to take any electrons away from iron. So the electrons can flow from lithium to iron, but they can't flow from iron to lithium because lithium's not strong enough. Iron is stronger than lithium. So what this means is there's kind of a metaphor I use, or a statement I use, that electrons fall down the activity series. They'll fall from a higher element, say lithium, down to one that's lower on the list, iron. But they can't go up the activity series. They can't go from iron, which is stronger, up to lithium, which is weaker. So let's look at an example. Let's take zinc and calcium. If you look at your periodic table of ion charges, or charge numbers by ion, you will see that zinc and calcium both have a 2+ charge, and that chlorine has a 1- charge. So chlorine wants to gain an electron to be like the nearest noble gas, which is argon. Calcium wants to lose 2 electrons to be like the nearest noble gas, which is also argon. And zinc, now zinc is a transition metal. You can't figure out how many electrons it's going to want to lose, but you look at the charge number by ion sheet that you have, and it will tell you that zinc is also a 2+ charge. So let's look at how zinc and chlorine form an ionic bond. So this is a review of ionic bonds and how they form. Chlorine wants to pick up an electron, 1 electron, so it has a 1- charge. Zinc likes to give up 2 electrons, so it has a 2+ charge. So when zinc gives off 2 electrons, chlorine is going to catch those, but each chlorine can only catch 1 electron. Chlorine can only take a 1- charge. So you're going to need 2 chlorines to catch the 2 electrons that are given off by the zinc. So 1 zinc throws off 2 electrons, and each chlorine, you have 2 chlorines, catches 1 of those electrons. So you end up with zinc being a 2+ charge, chlorine being a 2 times -1, which is -2 charge, 2- charge. 2+, 2- are electrically neutral. They balance each other and they form a bond. So it's ZnCl2. You need 2 chlorines for every 1 zinc. Calcium will do exactly the same thing. Calcium likes to give away 2 electrons. Chlorine likes to gain 1. So if you have 2 chlorines, it can catch the 2 electrons that were given off by the calcium. So calcium gives off 2 electrons. Each chlorine catches 1 of those. So you have a 2+, 2- charge. So you have calcium chloride. So both zinc chloride, ZnCl2, and calcium chloride, CaCl2, can form. They're natural ionic bonds. So now let's look at the reaction down below. You have zinc chloride, and you put in a solution, and we're going to talk about solutions, but it's in water, and you're going to put it in water, and then you're going to mix in some calcium, some Ca. So remember, the zinc is a +2, the chlorine is a 2-, so those balance to form a bond. The calcium right now is electrically neutral. It doesn't have any charge. It's just a calcium atom, just the way it was born, with no charge, with the same number of protons as electrons, so it has no charge. So what happens if you look on the right side of the arrow is somehow the zinc came away from the chlorides, the Cl2, and the calcium took its place. Now the calcium is bonded to the chlorides. Now how did that happen? Well, calcium started off with a 0 charge, zinc with a 2+ charge, and the two chlorides together have a 2- charge, so 2 + 2- balances, and they attract each other. Then the zinc suddenly has a 0 charge. Now how did that happen? Well, zinc had a 2+ charge because it had lost 2 electrons to chloride. So zinc is now a 2+. It's within that ionic bond, but it now it's lost 2 electrons. Now, since zinc is lower on the activity series than calcium, it can attract 2 electrons away from calcium. So calcium has its orbitals are filled with electrons. It's all the electrons it's supposed to have, but it gives up 2 of those to zinc. So what happens when zinc gains back those 2 electrons that it had lost to chlorine? It then becomes electrically neutral. It has the same number of electrons as protons at that point, which means it's no longer charged by 2+ charge. It's now neutral, so it breaks away from the chlorine because there's nothing to attract it to the chlorine anymore. It doesn't have a charge to it. Meanwhile, the calcium does have a charge. It gave up 2 electrons to zinc. The calcium lost 2 negative charges, 2 negatively charged electrons, so it now has a 2+ charge. So that means now the calcium is going to be attracted to the chlorides, the 2- over there. So effectively the zinc and the calcium trade places. So let's say that one more time. Zinc starts off in the ZnCl2 compound. It's lost 2 electrons to chlorine, and that's why it forms the bond. But it can gain those 2 electrons back from calcium. Why? Because zinc is stronger than calcium. It's able to pull electrons away from calcium. So zinc pulls 2 electrons away from calcium. It now has its full complement of electrons. It has as many electrons as it has protons, so it's electrically neutral. That means there's nothing to attract it to the Cl2 anymore because it doesn't have a charge to it anymore. Meanwhile, the calcium gained a charge. It lost the 2 electrons. It now has a 2+ charge, so now it's going to go over and be attracted to the Cl2. And so effectively what happens is the calcium and zinc trade places, and that's called a single replacement reaction. And there you see over on the right is the Ca now has a 2+ charge because it gave up 2 electrons to zinc, and the chlorine always had a 2- charge there, so that's where you end up. So on the reactant side, the left, the calcium atom is electrically neutral. The Zn is a 2+ cation in the ionic compound ZnCl2. On the reactant side, the left, the calcium atom is electrically neutral, so we just made that statement. On the product side, the right, calcium passes 2 electrons to zinc. This gives zinc a 0 charge and calcium a 2+ charge. This causes calcium to trade places with the zinc, and calcium forms an ionic bond with chlorine. So it's now calcium chloride. So think electrons fall down the activity series. So if the neutral element, this is the thing you got to remember if you just want to know what's the rule. If the neutral element, the one that was on the far left side, is above the cation on the reactant side, the reaction will take place. So let's look at some examples here. So use the activity series to determine if each single replacement reaction will take place. Okay, so Ca is the lone element. It's electrically neutral. Then you have zinc chloride, and then does that reaction happen? So what we're going to do is look at our activity series table as we do each of them. Okay, so remember the weaker guys are on the top. Those are the ones that easily give up electrons and don't do a very good job of pulling in electrons. These down here are stronger than the ones on the top. They do a better job of pulling in electrons. They don't easily give up their electrons. So the guys on the bottom will pull electrons away from the elements on the top. So we said if calcium is above zinc, so there's calcium, and down here is zinc. If calcium's above zinc, then the electrons are going to fall down the activity series to zinc. They fall down because zinc is stronger than calcium, so it can pull electrons away from calcium, and calcium is weaker. It will give up the electrons to zinc. So that reaction will take place where calcium passes electrons to zinc. So the answer is yes. Calcium is above zinc on the activity series, so that reaction will take place. Let's look at the next one. Now this is just the reverse of number 1. Zinc plus calcium chloride produces calcium as a lone element and zinc chloride. So it looks like this reaction could take place. There's no reason just looking at it why you would say that reaction can't take place. But we have to see where zinc is on the activity series, so we're going to go do that. Okay, so we see zinc is the lone element in that reaction. It's the one that starts off by itself. If the lone element is below the one that's in the ionic bond, in this case it was calcium, that reaction will not take place. So the electrons cannot go from zinc up to calcium simply because zinc is stronger than calcium. Calcium can't pull electrons away from zinc. So electrons don't go up the activity series list here. So the answer is no. That reaction will not take place. So the answer is no. Zinc is below calcium on the activity series. That reaction won't take place. Let's try another one. K is potassium, Ag is silver. So potassium is the lone element. It's electrically neutral. Ag is the metal. They're both metals. And then fluorine is the nonmetal that's creating an ionic bond with silver. So silver, AgF is silver fluoride. So the question is, will silver pull an electron, 1 or 2 electrons away from potassium, from K? And will K give up its electrons to Ag and therefore create that reaction where the potassium then becomes ionically bonded to the fluoride and the silver becomes a lone element outside? Okay, so let's go and check that one. Okay, so we find potassium, and potassium is right here. Okay, so it's very high. That means it's very weak. It will easily give up electrons, and it won't do a very good job of pulling in electrons. Silver's way down here. Okay. Silver's stronger than potassium. So silver can pull 1 or more electrons away, really 1 electron away from potassium. So the electron, the one that's the lone element outside, in this case potassium, will fall down the activity series to silver. So silver will pull that electron away, and therefore that reaction will take place. Okay, so since K is above above Ag, since K is above Ag on the activity series, the reaction will take place. The reverse reaction, Ag plus Kf going in the other direction, will not take place because Ag is below K on the activity series. Let's try another. So nickel, Ni. So we have to find nickel and magnesium, Mg, on the activity series. If nickel is up above magnesium, that reaction will take place. If it's not, if magnesium is above nickel, the reaction will not take place. So let's go look for that one. Okay, so here's magnesium right here, and here's nickel down here. So nickel was the lone element. So if it's above magnesium, the reaction will take place. If it's below magnesium, which it is, the reaction will not take place. Nickel is stronger than magnesium. Magnesium is not going to be able to pull electrons away from nickel, because nickel is stronger, so the electrons don't go up the activity series like that. Therefore, that reaction will not take place the way it's written. Okay, so the answer to that one is no. Nickel is below Mg on the activity series, so that reaction will not take place. The reverse reaction would, if you had nickel oxide, NiO, plus magnesium, which you see on the right side, those would switch places because the nickel would be able to pull electrons away from the magnesium, and you would end up with nickel plus magnesium oxide. So the reverse reaction will work, but not the reaction as it's written there. Let's do one more and we'll wrap up this lesson. So Sn is tin, Ba is barium. So Sn plus BaO, will that reaction take place? Will the Sn, will the tin trade places with the barium? So let's go look and see where tin, if tin is above barium on the activity series, the reaction that you see there will take place. If tin is below barium, the reaction will not take place. Okay, so let's find tin. Here's tin, and here's barium. So barium is much weaker than tin. Tin is much stronger than barium. So barium is not going to be able to pull electrons away from tin. Tin is below barium on the activity series, so that reaction, tin was the lone element in that reaction will not take place. So there we see no. Tin is below barium on the activity series, so the reaction won't take place. So again, if the lone element that you see on the far left side of the equation, the Ca, the Zn, the K, the NiSn, if it's above the element that's in the ionic compound, the reaction will take place. If it's below the element in the ionic compound, that is the metal that's in the ionic compound, the reaction will not take place. And so that wraps it up. That's just a quick overview of different types of reactions, and it's how you use the activity series to determine whether a single replacement reaction will actually take place. So I've given you a short assignment. Hope maybe you can get this done before we even go on break. I've tried to keep it very short. Just identify some reactions and also identify whether certain single replacement reactions will take place, okay? Other than that, you enjoy your vacation and get caught up on things that you're behind by over the break. I will have some tutoring hours over that, and I'll be sure that you know when those are. Okay, so have a good day, and I'll see some of you in class, and have a good break if I don't.